Today I will talk about your strain. Okay, in the last lesson we have learned what is stress and how to calculate it, and the stress caused by your tensile force as well as compressive force and your shear force. Okay, so in this video we will learn how to calculate strain and also how to visualize what is this strain actually is. Okay, so again go back to that previous diagram where we had a bar like this. Okay, and this bar was subjected to a tensile load. Okay, so now what was the result of this tensile force P on this bar? Well, the first result was that it will stretch. Okay, and if we consider that this bar is composed of infinite number of longitudinal fiber like this, each fiber tends to stretch. Okay, so what will happen if you remove this load? Simply it will go back to its initial position, correct? So initially, let's say after application of this load, the shape become like this. Okay, after stretch, and once you remove the load, again it goes back to its initial position. Okay, and this going back, or when you remove this load, the deformation, let's say this delta, it may be removed completely. Okay, or it may be removed partially. Okay, and if this deformation remove completely after removing this external load, in that case the material is known as your elastic material. Okay, and let's say there is some deformation, or you can say that it has removed partially. In that case the material is known as your partially elastic. Agree? And now in this discussion we will assume that all the material we are dealing with are elastic material. Okay, so normally the material that we deal in our engineering life is steel or concrete. Okay, this material are elastic provided that you are applying a load that is not causing this deformation too much. Okay, that means that if this deflection delta is small, in that case the material that we used in our daily life as civil engineer, that is your steel and concrete, they behave elastically. Okay, so in to understand this strain concept, we will assume that all the material we are dealing with are elastic material. Clear? So now we have understand what is elastic material, what is fully elastic and partially elastic material, and when this fully elastic material concept valid. Okay, and now we are going to define your strain, what is strain actually is. Okay, so here let's say initially the length of this bar was say L. Okay, and once you apply your external load P, the deformation is delta. Okay, or the stretch in each and every fiber, that is delta. So what is strain actually? The strain is defined as the ratio of this deformation delta with respect to the actual length of this bar. Okay, here it is L. So what is the unit of this strain? Definitely the deformation delta is maybe your, let's say, inch or meter, and also the length of your bar is also in inch or meter. In both cases you can see that they are cancelling each other. That means your strain is a non-dimensional quantity. Okay, so strain is a non-dimensional quantity. So now it is clear to you what is strain actually is, and now we will try to understand the interrelation between the stress that we have learned in the previous lesson and the strain that we have learned just now. Okay, so in the previous lesson we have learned that stress is, what is stress? The stress can be expressed mathematically by the ratio of this external force P divided by the cross-sectional area of this member. Let's say if this is the cross-sectional area, it may be anything, any arbitrary shape, and we are assuming that the cross-sectional area is A. Okay, so this is stress and this is strain. Now how to correlate them? Okay, so as an engineer it is our duty to calculate that how much any bar will deflect under the application of your external load. How much? What is the value of this delta? Okay, so if you are asked what is delta due to this external load P, so you can say from different experiment that this delta is proportional to this length. So more is the length of the bar, more is this delta, and also it is proportional to the force. Okay, that means more is the force, more is the elongation or the deformation, quite natural. And also it is observed that more is the cross section, less is the deformation, or less is the cross section, more is the deformation. That means it is inversely proportional with your cross sectional area. Now if we combine all these things, okay, all these three, if we combine all these three, we are getting that delta is proportional with your external load P, total length of the bar L, divided by the cross section of this member. Okay, so this is the delta with in relation with this P, L and A. Now if we remove this proportional sign, we have to use some constant. Okay, so delta is now is equal with we are using a constant, that is 1 by E times again P times L divided by cross sectional area. Okay, so this is the deflection due to external load P on a member whose length is L and yes, cross section is A. Okay, now we have two more formulas here. You can see that first one is strain formula, okay, and second one is stress formula. Now my wish is to replace this stress and strain into this equation. Can you do it for me? Well, just simply pause and try to do it yourself. If you cannot, obviously I am here for you. Okay, so hope you have tried. Now come back again. So our delta is nothing but 1 by E times P by A. Okay, I am using P by A in one color and L in another color. Okay, again, well, let me use E in different color. Okay, So this is E. Now if I rearrange this equation, that is delta by L in one side is equal to 1 by your E remains constant and into P by A. Okay, so is there any similarity? Yes, here you can see P by A is nothing but your stress, and delta by L is nothing but your strain. So simply replace them. Delta by L becomes strain, that is let's denote strain with epsilon and denote stress with your, let's say, sigma. Okay, this is sigma. So here strain is equals with 1 by E, that is constant, times sigma, that is P by A. Okay, so here you can see that strain can be expressed in terms of sigma. Okay, and not only that, here you can see that your strain is proportional with stress, or your stress is proportional with your strain, and that is known as your Hooke's formula. What is Hooke's formula? Hooke's is saying, this is very famous formula, Hooke's law, that is stress is equals with E times epsilon, where sigma is stress and epsilon is your strain. This is the famous Hooke's law, and just now we have learned how this law has been derived. Not only that, if you plot this equation, it will look something like this. Okay, so let's say this is the axis which represent your stress, and this is the axis which represent your strain. Okay, so if we draw the curve, it looks like this one. Okay, something this, and here you can see that the slope, okay, let me use a different color. This slope, this is nothing but your cross section, sorry, constant E. Now what is this E? Well, this E is known as your modulus of elasticity. Okay, so what is modulus of elasticity? This is the ratio of stress by strain. Now if epsilon is 1, in that case E is equals with sigma. Agree? So now if I ask you how to visualize this E, can you do it? Yes, definitely you should be able to do it. Let's do it together. Okay, so this is E, which is equals with sigma if our strain is equal to 1. Okay, so we have to apply a certain amount of stress to a material or to a member, structural member. We have to apply a stress sigma so that it elongated, the deformation is just equals with its length. So here delta is just equal with L. So what is the strain in this case? This is strain is equal to delta by L. Agree? And here delta is equal to L. So L by L is equal to 1. And now epsilon is equal to 1. That means E equal to stress. So modulus of elasticity is the amount of stress that need to be applied on any body to deform it with the equal amount of its length. Can you imagine? So if this is a bar, now you have to apply a load P so that it elongated like this, it becomes twice. So how much force or how much stress is required? Can you imagine? That is the reason E is always so much high. So what is the modulus of elasticity or E for steel? What is that? Let me know in the comment section. That's all for today's lesson.